Imagine you're teaching a robot to sort fruit. You show it an apple and ask, "What is this?" But the robot, being a cautious learner, doesn't just say, "apple." Instead, it gives you a list of probabilities. I'm 70% sure it's an apple, 20% sure it's a pear, and 10% sure it's an orange. Now you know the correct answer is apple. So the robot's top guess is right. But how do you give it a score? How do you create a system that encourages it to be even more confident next time without just guessing wildly? This is the exact challenge that AI models face every single moment. The answer lies in a beautiful piece of mathematics called categorical cross-entropy. It's the engine behind image classifiers, the heart of the large language models you interact with daily. And today we're going to understand it from the ground up. And more importantly, we'll explore what happens when this powerful engine runs into trouble and the clever solutions engineers have designed to fix it. Let's get started. First things first, let's move from a simple yes or no choice to a world of many options. Imagine we're classifying images into 3 categories: a cat, a dog, or a bird. How do we tell the AI what the correct answer is in a way it can understand? We use something called one-hot encoding. It sounds technical, but it's super simple. We create a vector, which is just a list of numbers, with a 1 in the position of the correct class and zeros everywhere else. So if we show the AI a picture of a dog, which is class 1, the ground truth vector, which we call y, is 0, 1, 0. This is the absolute, undeniable truth. Now the AI processes the image and, like our fruit sorting robot, gives us a list of probabilities. It does this using a special function at the end of its network called Softmax. All Softmax does is take the model's raw scores and squash them into a neat probability distribution where all the numbers add up to 1. So the model's prediction, which we call y hat, might be something like this: 0 at 25, 0 at 60, 0 at 115. This means it's 25% sure it's a cat, 60% sure it's a dog, and 15% sure it's a bird. Now we have the truth, and we have the prediction. How do we calculate the penalty or loss? This is where categorical cross-entropy comes in. The formula looks a bit scary at first, but the one-hot encoding of our true label makes it incredibly simple. The formula multiplies the true value with the logarithm of the predicted value for each class and sums them up. But since most of our true values are 0, they just wipe everything out. We are only left with the term for the correct class. So the loss is simply the negative logarithm of the probability the model assigned to the right answer. In our case, that's negative log of 0, 60, which is about 0.5v1. That's our penalty score. Let's see how this plays out. If the model is confident and correct, say it predicts 0.01, 0.98, 0.01 for the dog picture, the loss is negative 0.98, which is a tiny 0.02, a very small penalty. But what if it's confident and wrong? Say it predicts 098, 001, 001. The loss is nidus log 001, a massive penalty of 4.6. CCE brilliantly punishes the model for being confidently wrong. Nowhere is this more important than in large language models. At its heart, an LLM is a next token prediction machine. Given text like "the cat sat on the," its only job is to predict the very next word or token from a vocabulary of maybe 50,000 possibilities. This is the ultimate multi-class classification problem. The ground truth is a giant one-hot vector with a 1 at the index for the word mat. The LLM produces a 50,000-long probability vector. And categorical cross-entropy calculates the loss based only on the probability the model gave to mat. This happens for every single word, in trillions of words of text, guiding the model to become the powerful communicators they are today. But CCE isn't perfect. It has a few cracks in its crown. For one, it's a bit indiscriminate. It only cares about the probability of the correct answer. It's just as happy with the prediction of 0.163 as it is with 0.3 to 0.6, 0.1, because it only sees the 6. But you could argue the first prediction is better. It also encourages overconfidence. Pushing the model to make the correct probability 1.0 can make it brittle and less able to generalize to new data. And what if the training data itself is wrong? If an image of a dog is labeled cat, CCE will punish the model for getting it right, forcing it to learn the wrong thing. This brings us to one of the biggest challenges in all of AI: Class imbalance. Imagine you're building a model to detect fraudulent transactions. For every 10,000 transactions, maybe only one is fraud. This is a severe imbalance. If you use standard CCE, the model will quickly learn a clever trick to get a low loss. Always predict not fraudulent. It will be 99% accurate. But it will be completely useless because it will never catch the one case it was built to find. The voice of the rare fraudulent case is drowned out by the roar of the common legitimate ones. So how do we fix this? One of the simplest solutions is weighted cross-entropy. We give the loss function a cheat sheet. We tell it that making a mistake on the rare fraud class is way more costly. We assign a weight to each class, inversely proportional to how often it appears. This forces the model to pay attention. It can no longer afford to ignore the fraud class because the penalty for getting it wrong is now massive. It's like a professor making the final, most important question on an exam worth 90% of the grade. You're going to study for that question. But we can get even more sophisticated. Enter focal loss. This brilliant idea argues that the problem isn't just about rare versus common classes, but easy versus hard examples. Even a rare class can have some easy-to-classify examples. Focal loss says, let's stop wasting time on examples the model already finds easy and focus all our attention on the ones it's struggling with. It does this by adding a dynamic modulating factor to the CCE formula. If the model is very confident about a correct answer, this factor becomes tiny and almost erases the loss for that example. But if the model is struggling and has low confidence, the factor is large and tells the model, pay attention, this is important. This is like an expert teacher who doesn't give every student the same attention. They dynamically see who is struggling with which specific problem and dedicates their effort there. Focal loss allows the model to focus its learning capacity on the rare and difficult cases that truly matter. Now let's tackle that overconfidence problem. Standard CCE pushes the model to be 100% certain, but what if we told it to be a little less sure of itself? This is the idea behind label smoothing. Instead of using a hard, one-hot label like 010, we soften it. We take a little bit of the probability from the correct answer, say 10%, and distribute it among the other classes. So our new target for the dog image becomes something like 0.05.9, 0.05. We're now telling the model, it's very likely a dog, but acknowledge that there's a tiny chance it could be something else. This prevents the model from becoming brittle and helps it generalize better. It's like the difference between a naive student who says, the sole cause of the war was X, and a sophisticated historian who says the primary cause was X, but other factors also played a role. Label smoothing encourages our AI to become that nuanced historian. Finally, what about that massive computational problem in LLMs? Calculating the Softmax over a 50,000-word vocabulary at every step is a huge bottleneck. This is where a technique called noise contrastive estimation, or NCE, comes to the rescue. NCE cleverly reframes the problem. It asks, why force the model to rank the correct word against 49,999 others? What if we just teach it to tell the difference between the real word and a few fake noise words? It turns an expensive multi-class problem into a cheap, binary, real versus fake problem. It's like identifying a suspect in a police lineup. Instead of comparing a photo to every person in the city, you just bring in the real suspect and 15 random people. The detective's job is now simple. Point out the one who matches the evidence. By doing this millions of times, the model learns to spot the right token without the crippling computational cost. So, while categorical cross-entropy is the elegant default engine for AI decision-making, real-world success often comes from knowing its limits. Techniques like focal loss, label smoothing, and NCE are the specialized tools that allow us to build AI that is not just powerful, but also fair, robust, and efficient. By understanding the right tool for the job, we move from being just users of AI to becoming architects of better, more intelligent systems. Thank you for joining me on this journey into the heart of AI decision-making. If you enjoyed this explanation and want to keep learning with us, be sure to like this video and subscribe to Returd. I'm Amy, and I'll see you in the next one.